Hi, everyone. Hi, everybody online. So it's a pleasure to be here at GERAD to introduce myself and my recent work. I will start with a brief bio sketch. Okay. Concerning my academic background, I did all my studies at University of Montreal, actually here in Stat. I have a bachelor degree in pure mathematics. Then I did an applied master degree at the crossroads between finance, mathematics, and computer science. Then I switched completely into computer science at the PhD level with a specialization in statistical learning. And I was working under the supervision of Yoshua Benjo. And during my studies, I gained an expertise at merging parametric and non-parametric methods. The non-parametric methods in machine learning, such as mixture distribution and neural network, are useful in the central part of the data to model the data when there's a lot of data without a lot of strong assumptions. But they might be limited when we want to extrapolate beyond the range of the data. And this is why it might be useful to merge them with techniques from extreme value theory, which makes some parametric assumptions for the extrapolation. I would like to point that I don't think I have a very conventional background as a statistician, since I came to statistics through the back door of machine learning. Okay, this is not the right direction. So after my studies, I went to France. I was lucky to have a scholarship, and I went 2 years to work near Paris at Olivet with Philippe Navo. So you see, it's been a long time that we know each other. And my goal to go there was to gain more knowledge on extreme value theory, and also to switch from applications in insurance and finance to applications in time math and environment. And this was a really nice place to do that and to meet a lot of people. After 2 years, I went to Grenoble to work at Henry-Aronald with Stéphane Girard on a similar topic. And I had to interrupt actually this position because I gained a permanent position at IRD. This is the Institute for Research and Development. It is a French research institution, very similar to CNRS. CNRS, I think, is more well-known. In addition to a scientific endeavor, IRD aims at building capacity in developing countries, in particular in the Mediterranean area. So I was for 10 years at Agrosciences Montpellier in the south of France, working mostly with hydrologists. And then I went for 2 years in Tunis. And I was supposed to stay another 2 years, but I came back to Montreal, like Olivier said. I have my position at Polytechnique just for 2 years now. So it's been really exciting to come back in Montreal, in my home city, as a professor. So that's it for my bio sketch. I'm going to go now to my scientific presentation. I'm going to start with a mathematical example. So the trick now is the animation going to work. So that's okay. So I'm going to talk about hazard indicator for flood risk. And here it's a simple hazard indicator is the water depth, so the water level in a street. So this is a fictitious street, the main street and lateral street, and these are buildings where you see planks. And the way the data is generated with hydraulic models. And these models, they rely on physics equation, and they are very useful to provide information on the flow propagation in complex geometries, for instance, in urban areas. So this data, it's not very easy to see with the color, but it's at a uniform level. The water is still at 1.5 meter. And as I move the animation, you can see better all the high resolution cells. There are over 2,000 of these cells. And the water is now moving. It has a peak and the intersection. These two branches have higher water level, here lower, and this is going to propagate. So these types of hydraulic models, they can simulate very complex data, and very precise and useful. However, the computation time is very long. For instance, it could be longer to simulate, the simulation time can be longer than the time simulated, so they are not very useful for operational purposes. Okay, so the main objective of our work is to provide an approach to speed up computation times. And we have chosen to develop an extension of material resolution analysis. It's actually a type of discrete wavelet approach. And we provide an extension for the spatial-temporal framework. In particular, it works for irregular data. So there are two sub-objectives. The first one is to use this framework to provide a representation for this data, which is actually exact and non-parametric. And second, based on this representation, we propose a conditional non-parametric model. For this model, I'm going to use as a covariate, if you want, low resolution hazard indicators. So these hazard indicators are faster to obtain because they are computed on a low resolution grid. And my goal is going to be to predict high resolution hazard indicators, so the one that I've shown you at the beginning, which can display, as you have seen, very important nonlinear spatial features, in particular, which are non-stationary and non-isotropic. So the conditional model goal will be to simulate these high resolution hazard indicator based on the low resolution data. So in a way, this model aims at performing downscaling of spatial disaggregation. So now I'm going to move into the details of our extension of the multi-resolution analysis framework. So in multi-resolution analysis, usually we work with a temporal, we can work with a temporal signal where each element is a time step, or we can work in 2D with an image where each element is a pixel. But in this case, we have a spatial temporal data. So each element is actually a time series at a given location. So in my particular example, an element is one of my high resolution cells. And there are 16 time steps. So it's a vector with 16 values. And the multi-resolution analysis scheme works with 3 steps that we have adapted for the spatial temporal framework. The first one is the split step. So the goal of the split step is to divide all the elements into groups and in 2 categories, predictors and responses. And it's going to become clear in a minute, in a second, why we call them predictors and responses. What we want to is to select the elements that are the predictors as close as possible to the responses. The second step is called the predict step, and it's actually doing a local regression. And in the local regression, we want to predict the responses from the predictors. So I wanted to say, traditionally, the responses and predictors are called even and odd elements. But in the spatial temporal framework, it doesn't really make sense. And this is why we stick to this terminology. So once we have performed local regression, we record the prediction errors and we put aside the responses. So the prediction errors are, in fact, regression residuals. And in the multi-resolution terminology, these are termed wavelet coefficients, and they are, in fact, details of the signal. The third step is the update step. And the goal of the update step is to account for the fact that we put aside all the response elements. So it's basically an average operation, and it's going to yield what is called scaling coefficients. And these are a smoothed version of the signal. So once we have performed these 3 steps, we can iterate these steps, and we start again from the smoothed version of the signal, which is provided by the scaling coefficient. So I'm going to illustrate these algorithms on the data that I've shown you at the beginning. So this is the split step for stage 1. So we start with n elements, and our goal is to group them into groups or 2 or 3 elements. So classically, it's a group of 2 elements with 1 predictor and 1 response. But to extend this to a non-dyadic number of 2, we allow sometimes to have 2 response elements. So here you see the results. Of course, there are lots of groups, so it's hard to see them. But most of the time, when you see 2 points of the same color, which are nearby, it means this is a group of predictor and a response. And if there are 3 of them, that doesn't happen very frequently, but it means we have a group of 3. So we start with n, which is about 2,000 elements, and our goal is to obtain about half the number of groups. So to do this, one of our contributions is to use clustering. It would be very difficult to use clustering and to obtain exactly this number of groups with each group with 2 elements. So what we do is we do a clustering with a number of groups which is smaller than half the number of elements. But we want it to be as large as possible to capture as many details in the flow. But we want also to make sure that there are at least 2 elements. So once we have that, we can just split each cluster sequentially. And why we do this, because each cluster, by definition, all the elements in each cluster are very close to each other in values. So we can just fit them sequentially. It doesn't really matter in which order anymore because we know they are close in values. So we take pairs of predictor response in each cluster. And if there's an odd number of elements, the last 3 elements will be a triplet. So 1 predictor and 2 responses. So I just want to point out now the groups of predictor and responses, since they are taken within each cluster, they do not cross any cluster boundaries, so they do not cross any important feature of the flow. And this is going to be important to have small wavelet coefficients. So this is the illustration of the predict step for stage 1. So in this case, remember, we want to predict each response from a predictor, and we record the prediction errors and we put aside the responses. So these are the results for stage 1. You see gaps for the predictors, and the prediction errors are shown for each response element. I'm showing the temporal median because remember, we have 16 time steps for each location. So we have a larger number of response elements than half the number of elements. This is because of the clustering scheme that I have described before. So how does this work? For this predict step, we use a very naive predictor. Actually, we predict the response just by X. And then we need to perform to compute the residuals, very simple subtraction operation. And D is the wavelet coefficient. It stands for details. When there are 2 responses, I just need to do the computation twice. Very simple computation. So now the third step is the update step for stage 1. I need to transform the predictors to include the volume of my responses that I'm leaving aside for the next stage. Basically, it has a smoothing effect on my data. So here I'm showing the scaling coefficients values, but over the group, this is why you don't see any gaps, okay? And there are, the number of scaling coefficients is a bit smaller than half the number of elements, again, because of the way that we do the discrete step. So for the computation, very simple computations again, to compute the scaling coefficients, we just need to compute an average. So it's an addition. I can express the scaling coefficient C in terms of the details, so the regression residuals. And if I have 2 responses, I can just adapt the way that I compute the average. So it's very easy operations to obtain, to run our algorithms. And then I can go to stage 2. To go to stage 2, I'm going to start from these scaling coefficients from the stage 1. I have the number of elements that I had at the beginning. So at some point, I'm not going to be able to iterate anymore because I'm going to be left without any elements. So I'm not going to go to stage 2. I'm going to jump to stage 4 to show you what's happening. So this is the aggregated partition of the split step. So it accounts for the partitions of all the previous steps. And contrary to stage 1, we start to see the propagation of the flow, which is oblique, as you have seen in my data. Here are the wavelet coefficient, the temporal median, with the most information is in the central part. And then the update step, which is a smoothed version of the signal. I think it's becoming more visible here at stage 4. I'm going to show you the next stage is stage 8. So again, the split step now it has only 6 partitions, so it's aggregated partition again, and we see just the main feature of the flow, the oblique propagation, the wavelet coefficient, and then the scaling coefficient, which provides a smoothed version of my signal. So yeah, see with very simple operation, I'm able to decompose the signal with each stage that corresponds to a resolution level, and the higher the stage number, the more smooth the image, so the lower the resolution level. Okay, so now I have all the elements to address objective 1 is to provide a representation for the spatio-temporal data. So to this end, we run the multi-resolution analysis that I've shown you before. So I'm going to run as many iterations as I need to end up with a single element. So if I start with a number of elements n, which is the power of 2, I'm going to need to run my 3 steps for n stages. So my notation for my signal S is SIT. So this is the signal. So my water depth that I've shown you at the beginning. I is the location. So this is my high resolution cell. And T is the time step. It varies between 1 and capital T. And once I have run my material resolution analysis for all my n stages, then the last element is just the spatial average at time t. Okay, so it contains by definition no spatial information. All I know is the spatial average for a given time step. And then if I gather together all the wavelet coefficients from all the stages, I'm going to have n-1 wavelet coefficients. So this can be very high dimensional. I denote them dkt. And this is going to be where the information on the spatial pattern is in my model at time t. And then the other information, the other quantity I have are geometry coefficients. I call them alpha k. So alpha k varies is of dimension n. It varies with the spatial information, so with the location, but it does not vary with time. So we're going to assume that this coefficient, they represent the configuration, the hydraulic configuration, and they depend also on the way the partitioning is done. And we're going to assume that these are fixed. So the only information on the spatial structure that varies with time is given by the dkt. If I combine all this information, all these 3 quantities together, I can obtain an exact spatial temporal representation for the signal at time t. So this is the signal at time t for all the spatial location, so the n high resolution cells. So my signal at time t is equal to the spatial average and a linear combination of my wavelet coefficients with weights provided by my geometry coefficients. So this is an exact representation, and I'm going to use it to build my conditional model.
What's the meaning?
Sorry?
What's the meaning?
It means transpose.
Oh, okay.
Yeah,
Transpose.
yeah, nothing special.
And which is that?
15.
50. This all of shapes are always symmetric according
This
to
one here?
diagonal line. With this one and this one, as we compare, that there is no, symmetric.
It is symmetric, and this is because it's a good point. It's because this is a feature of the flow. And here, actually, it's hard to see, but there are only 6 scaling coefficients. So basically, there are just 6 values, but I'm showing the values over the cluster group here. So here, really, we just have 6 values, but I'm showing their value over this partition. This is why you get the impression that it has the same symmetry. It's the way it is constructed, actually. And why we have this symmetry here is because of the hydraulic feature of the flow. That's clearer? Yeah. Okay, so this is the representation that we derive from our materialization algorithm with these 3 quantities we're going to use to build the conditional model. So sub-objective 2, the conditional model, we're going to assume that there's only a discrete number of spatial patterns. I'm going to explain how we do that. So to build the conditional model, the first thing that we need to do is to run the material resolution analysis that I've explained just previously on the high resolution data that we have available for training. So for a given hydraulic configuration, and this is going to yield the geometry coefficient alpha k. So these coefficients, they just depend on the hydraulic configuration that we assume is known ahead of time and on the way the partitioning is done in my split step. And I'm going to assume that this is fixed for all the other scenarios that I can have. Then I have also a set of wavelet coefficients that can be very high dimensional. Remember, this is of dimension n-1. And in the case I have shown you is over 2000. So this can be very high dimensional. How we deal with this is that we build a basis of what we call spatial pattern types. So the spatial pattern is provided by DTs, but what we do to be able to deal with the high dimension is that to deal with the high dimension, we perform compression And this is what wavelets are used for usually. And we reduce the dimension of ET with compression. And then we perform clustering on the reduced wavelet coefficients. And we use the prototypes of these clusters as spatial pattern types. Okay, so this is a way to reduce the complexity of the spatial pattern, which is contained in ET. And then the downscaling part is to use the low resolution data that we have, which is cheaper to obtain computationally, to estimate the three quantities that I need to build my, my representation that I've shown you at just the previous slide. So we need to estimate first the spatial average. So this in the general case would be a regression, but in our case, we can have actually an exact computation because we are in a perfect upscaling case. I will explain a bit better when I show you the results. Then we need also to estimate the spatial pattern types. So this is the trickiest part, and it is a classification task. And to this end, actually, we use a pretty classical feed-forward one hidden layer artificial neural networks for this task. And alpha k, we are going to assume that these are fixed. So if I have another simulation from the same configuration, I'm using the same geometric coefficient because nothing has changed spatially. And then we can use all this information to reconstruct the high resolution data based on the representation that I have shown you by combining these. Okay, so this is what we're doing. I'm going to show you the results. So this is an extended example. I've shown you just one intersection at the very beginning. It was here. Now I have 8 such intersections. So globally, I have about 16,000 high resolution cells. So it's pretty high dimensional. I have 2 hazard indicators. I've discussed only the water depth in meters at the beginning. We also have what I call run of speed, but the technical name is unit discharge norm. And each intersection is considered a subdomain. So subdomain is the size of the low resolution data. And the low resolution data is simply the exact average of the high resolution data. So this is the perfect upscaling case that we're doing. So this is the configuration, my synthetic data, main street, lateral street, and at time 0, there are 2 different water levels. On the left-hand side, it's about 3 meters. On the right-hand side, it's about 1. Well, I'm not really sure. Actually, I think in this case, it was actually 0. It depends on the initial conditions. There are several ones. Okay. So we have several flow scenarios. The flow scenarios are defined by the boundary conditions. So these are the water level on the left-hand side and on the right-hand side at time 0. We have 3 flow scenarios for training. They are represented here. This is the 2 water level. And we have 3 flow scenarios for training. And then we have 2 flow scenarios for validation. So to choose the hyperparameters of our model. And we have 5 flow scenarios for the test set. These are the squares over here to evaluate the performance. And as you can see, most of the flow scenarios for the test are well outside the conditions that were seen for training or validation. So it's a pretty challenging setup. Okay. So on the left-hand side is the hydraulic data, time 0, and then it propagates across the street. I'm gonna stop it here. And so this is the water depth in meters. And this is our reconstruction on the right-hand side. So at time 0, it's always perfect. And then I'm showing you the propagation, which has the right patterns. Of course, it's just a visual assessment, but it's pretty convincing, I think. And I'm going to show you the results for the run of speed data. So I haven't shown you this data yet. On the left-hand side is the original data. So you're going to see the spatial patterns are a bit different, a bit more hectic, I think. So this is in square meter per second. And on the right-hand side, our reconstruction for this test set. So it's not perfect, but it's capturing the main feature of the flow. So I'm coming to an end for my presentation. My final message is that I didn't show you any quantitative measure, but we have them if you want to have them eventually. We also have a field scale case study, so a real urban configuration, which is derived from a Sacramento neighborhood, and the simulation of a dam breach in a dike that protects the neighborhood. We made some comparison with when we use PCA to learn the spatial pattern types instead of the material solution representation that I've shown you. And also we made a comparison, while sometimes PCA is performing similarly than the wavelet approach, but most of the time the wavelet approach is much more powerful. And we also made some comparison with classic interpolation schemes. So classic interpolation scheme would be, for instance, bilinear interpolation, but in our case, it's not applicable because the mesh is not regular. So I've used kernel regression instead. And in that case, the performance is really much lower. So the good news is that a couple of days ago, our article got accepted for publication. So if you are interested to know more about it, I would be very happy to share it with you. So thank you for your attention.